Hi everyone. Our team's research project is advancing forest fire production, integrating unit and drone imagery for enhanced risk assessment and management. Our team members are 子韵、堪宇仲 and 陈雷. For the problem, we have the problem description as follows. Our forest fire pose significant risk to biodiversity, property, and human lives. Traditional methods for protecting and managing these risks often fall short due to their inability to process vast amounts of data from diverse sources or adapt to the unique conditions of different forest areas. Our project seeks to leverage advanced machine learning models, specifically UNet, combined with the high-resolution drone captured imagery to predict the fire risks in our British Columbia with greater accuracy. By segmenting forest areas into actionable risk thresholds, we aim to provide customized solutions for various stakeholders, such as park managers, insurers, farmers, and the wine industry, thereby enabling more effective prevention strategies and resource allocation. For our whole plan, we have the 5 steps. The first one is collect data and then just train the network and then do the conversion from RGB to HSV, but we haven't decided yet if we need to use this one. And after that, we will apply the metric distance. As mentioned, we haven't decided yet, so which metric should be the best one. After that, we will do the simulation result. For the data collection, we just collect data by the drones, and then on the different scenarios as I mentioned, like the parks, like the national parks, the winery, and so on, and then we get the data set. For the train network, we just choose to use the UNet, but we haven't decided yet which one is the best because the family has the big ones. So the goal of the network is to just segment the target district from an image. And for the data set, like how we do the operation with the data set, we just divide the image samples according to the trained data set and the test data set. And we label the samples using the label me. For the train network, our target is the trees or the crops in the image samples. Those trees and crops are in the main combustibles in those districts. For the algorithms, for me, I'm doing the REST UNet++, which is an architecture that uses the strengths of deep residual learning and UNet. The proposed REST UNet++ architecture takes the advantages of the residual blocks, the squeeze and the excitation blocks, ASPP, and the attention block, and I will tell more in the next picture. I will say, like, for the architecture I have mentioned, I just talk something about the architecture before, and then I will see the future extraction, which just because it have the additional architectural components, so the REST UNet plus just does better for this part, and then because the REST UNet has the squeeze and excitation blocks, which allows focusing more on the relevant features by recalibrating channel-wise feature responses. And then for the attention mechanisms, which just improve the model's focus on more relevant parts of the image for the task. And for the accuracy, generally, the REST UNet just has the higher accuracy in the segmentation tasks rather than the traditional UNet one. So that's why I chose REST UNet++ for my at the models in the unit class, unit family. And then I will tell something about the implementation. I think first we need to just import some first thing we need to import some required libraries as I mentioned, because we use the Python to do that. And then we need to prepare for the dataset class. But those would be like the general steps. So I will not just mention more about those part. I just talk about the implementation for the very specific parts, like the implementation for the residual blocks, and then just integrate the squeeze and the excitation blocks, as I mentioned, because that's very specific for the REST unit. So I just do the 2 steps to do those things. After that, I just assemble the REST unit model. Yeah, this one is just because I have the unit the traditional unit architecture. So I need to just construct the REST unit model by integrating those residual blocks and the SE blocks into the unit architecture, and then that should be the assemble step. And after that, I just implement the training loop to do the train. After that, after we get something from the training loop, we can apply the different kinds of distance, and I choose the Mahalanobis and the cosine distance but as I mentioned, we haven't decided yet which one should be our final choice. After that, we just do the model evaluation and testing to choose the best one.
For my part, the model I use in my algorithm is called UNet 3 Plus. It has several features. The first feature is nested skip pathways. This allows the network to capture multi-scale features at different levels of abstraction. The second feature is dense connections. This can be used to connect multiple layers within each resolution level. This allows features to be spread more easily throughout the network and makes feature reuse easier. The third feature, attention gates, can help the model focus on relevant features such as fire and one-yas in my case, while filtering out irrelevant background items. The fourth feature is residual connections. So this one can address the disappearing gradient problem when training deeper networks. And now after learning about the model features, now let's take a look at the algorithm procedures. Just like my team members, my algorithm followed the similar steps. So I begin by collecting datasets relevant to the one sector in British Columbia and using LabelMe to label the images with one-year keywords. And after the dataset collection and pre-processing stage, the UNet 3 Plus model is assembled to train the datasets. We train the datasets by iterating over the datasets. And here you can see the basic implementation of the UNet 3 Plus architecture. And after assembling the model and training the datasets, the model's output comes out. And so for the model's output, it consists of RGB segmented matrices, which I convert to HSV format for calculating pixel color distances. And to quantify the differences between pixels, I use the Jacquard distance and cosine distance calculation methods. And here you can see the formula of calculating the Jacquard distance. And after using the methods, the fire risk probability can be obtained. And the last step in this algorithm is to define the thresholds and map various solutions to these different thresholds. And this is the step that we are still working on and will be working on in the future.
My algorithm generally follows the same structure as others. First, it starts from collecting dataset relevant to my target client, the forestry business owner, from a website named eStock. Then I use Label Me to label all the images for training. Because our group decided to use UNet model for this project, so I implemented and played a little bit with an improved UNet model called the Archer unit. I will come back to this model in my following slide. With my data labeled and trained, once I get RGB segmented matrices as output, I convert the output into HSV format and use a distance calculation method called Chebyshev distance to calculate the distance between pixels. So here is a little bit about the Archer unit. The differences between this model and this unit and the basic UNet model is that this one replaces the standard convolutional blocks with residual convolutional blocks and recurrent residual convolutional blocks. The RRCNN consists of two residual convolution blocks with residual connections versus the basic UNet model doesn't have residual connections between each layer. So here is the reference of the R2 UNet module block.
Use my algorithm following node steps. The first step is to collect data, collect image samples from specific scenarios. The second step is to train my framework, train image segmentation network using image samples. The third one is to transfer the RGB color space to HSV color space. Finally, I will use metric distance to get the threshold to get the result. Because my scenario is the farms in British Columbia, we'll use the drones to connect the images in the farms or around the farms. This is the network. I choose the basic UNet as my framework because we need to contrast many UNet frameworks. So I will get the result of the basic framework as the baseline. The UNet framework is to segment the target district from image. This is the code to train the framework of UNet. The left side is the structure of the UNet. The right side is the result I want to get, the segmented outputs of the algorithm. I need to divide the image samples according to train dataset, test dataset, valid dataset. We'll use train dataset as the input to train the framework, and then I will test the framework using test dataset and valid dataset. Before training the dataset, I need to label the samples using Label Me. As I said, my scenario is the farms, so I need to segment the trees or plants, crops in the farms. This is the HSV color space because in HSV color space we can compare two colors more directly than the RGB color space. So I need to transfer the RGB color space to HSA color space based on the values of RGB. Metric distance. Metric distance is our measurement to determine whether or not the two colors are the same. So I choose the cosine distance to get the distance to as my algorithm. This is the simulation plans. As I said, I need to choose the metric distance. My teammates maybe choose other metric distance. After we get the distance, we get the threshold. The different thresholds for different methods in our algorithm. So according to different methods, according to different thresholds, we can choose different methods to prevent forest fires. We need to choose the best metric distance because we need to make the similar piles closer and different piles further. So according to different scenarios, we use the same simulation plan to test the performance of different algorithm. We will choose the best algorithm from our algorithms. My teammates will contrast the result of their algorithm
with mine.
The aspects we took into consideration while working on this project mainly revolves around these 3 points. First of all is data privacy and security. The use of drones and management is often under strict regulations imposed by local governments. The area we collect data from may also impose issues of privacy violations to both individuals who happen to be in the frame or areas, communities that restrict from image collections. Therefore, we need to carefully navigate between restrictions, laws, and client expectations for each case. It also ties with our second point. If case requires, we need to be able to actively involve local communities and stakeholders to ensure everyone's perspective and concerns are taken into account. Transparency is about how we communicate with our clients. As a service provider, we need to be able to clearly explain our algorithms and plans, communicate with our clients about their expectations.
In conclusion, our team have worked collectively to address forest fire prevention and prediction in British Columbia, particularly in the fields of forestry, parks, winery, and farms. Our team members have developed customized algorithms and models such as R2UNet, UNet, ResUNet and UNet 3 Plus to analyze drone images for early fire risk prediction. By using various distance metrics to assess pixel color distributions, we can accurately segment areas based on fire risk probabilities. And for ethical considerations such as respectful data collection practices have been addressed to ensure the responsible use of technology. And moving forward, we will focus on refining our algorithms by determining the optimal model and distance metrics, establishing precise thresholds, and creating appropriate response strategies.